Okay, so for fluids, this is the buoyant force. Buoyant force. It's the force that buoys exert, right? Okay. What's interesting, though, is when you get these problems like this, right, and you've got some object under the water, right, you've got the buoyant force that's upward is rho vg, right? And this is the density of the fluid, right? Volume of whatever this thing is, right, times g, right? Of course, the force of gravity is just the weight of this. Well, the weight of this object is the density of the object, the volume of the object times g, right? The net force, and this is key, okay, the net force is going to be the difference in density times the volume times g. So this is something that will simplify your calculations. That's the net force. It's just the difference in density times the volume times g. We can make this really complicated, or you can kind of cheat like that. This is hydrostatic pressure. Okay, so if we've got a layer of water and there's a pressure up above this, right, and we're down here and you're in some fluid that has some density, right? This is just the pressure above it, plus this is the hydrostatic pressure. This is the equation of continuity. So if I've got a pipe that's big and then it narrows down, and we get a smaller area, right? If the area gets smaller, you go A1 V1 equals A2 V2. If the area gets smaller, the velocity gets higher. It's like when you put your thumb over the end of a hose, right? The water squirts out faster, okay? This is Bernoulli. Whoops. Bernoulli. Bernoulli. All right, and then this is the density of the fluid. That's the velocity. This is the elevation. It's the same thing here. They use D here, they use Z here. Go figure, okay? And then this is pressure. And the rows there are density. Whoops. That's density. This is also density, right? Or destiny, if you're like me. This is the drag force, right? So the Stokes force, if you've got an object, a small object falling through a fluid, right? It's got to be, I guess, spherical, right? The drag force is 6 pi. This is the viscosity. That would be Pascal seconds, I believe, right? This is velocity. R is the radius, right? And so these are, the problems, right? You can have an object falling through water, right? And so you can do this. You can say the difference in density, right, times the volume of the rock times G is equal to 6 pi viscosity, right? R, V, like that, right? Yeah, those problems, right? And then this is the Reynolds number. And the Reynolds number is basically, what is it? If it's above, if it's like 10,000, it's definitely turbulent. I think it's like 1,000, right? I think if R is bigger than 1,000, then we have, it's turbulent, right? We'll have to look that up, okay? This is our density. This is our radius. And this is, of course, the Reynolds number for radius. You have ones for diameter too, right? That's the velocity in meters per second. And then this is the viscosity. Okay. Is there anything else to say? I think that might be all we need to say.